Today we are joined by industry expert and HSC manager at Thales Australia, Adrian Sandrell. Adrian has over 20 years of proven experience across the manufacturing and mining industries in process safety management, maintenance management, failure investigations, root cause analysis, project management, and plant condition assessment. Prior to joining Thales as the HSC manager, Adrian held projects manager, maintenance superintendent, supervisor, and planning roles in the mining and manufacturing industries. So without any further delay, I will hand you over to Adrian.
Thanks, Bill, for the introduction. Now let's begin. I'm the Health, Safety and Environment Manager at Thales Australia, and I'm at the Mulwala facility. The quantities of hazardous chemicals and dangerous goods at the Mulwala facility significantly exceed the Schedule 15 threshold limits under the Australian Work Health Safety Regulations. The site operates as a licensed major hazard facility under those regulations, and we operate under the national regulator Comcare. The need for monitoring the effectiveness of safety management systems and the barriers used to prevent harm at a major hazard facility is well established. The diagram of the three main elements that make up a monitoring program have been adapted from the OHSAS 18001 standard, and it is specifically the need to monitor performance indicators that I will address today. The creation of performance indicators at the Mulwala facility started with the review of existing guidance. I've drawn heavily from some of this guidance material, as I will detail further throughout the presentation. Of course, there are many organisations that have done some very good work developing safety performance indicators. With every experience shared, the task for developing performance indicators gets a little easier. And it is in that context that I share some of our performance indicator journey with you today. The performance indicator examples that I will use are drawn from the HSE UK Guide for Developing Process Safety Indicators, HSG 254. This diagram has been taken from HSG 254, and of course we cannot talk to controls or barriers without also talking to the reliability of controls. The Swiss cheese model of accident causation is a model used in risk analysis and risk management. This well-known model, first proposed by James Reason, details barriers which are layered to provide defence in depth. As holes appear in safety barriers, like the holes in Swiss cheese, they eventually line up and allow a hazard to be realised. This is illustrated in the diagram borrowed from the HSE UK Guide for Developing Process Safety Indicators. Today, I will attempt to use entropy, the second law of thermodynamics, to further explain the holes in the Swiss cheese and the rate at which they expand. In the BBC documentary Wonders of the Universe, Professor Brian Cox builds sandcastles in the desert to explain entropy, the second law of thermodynamics. If we think of safety controls not as single things, but as being made up of many constituent parts, like individual grains of sand in a sandcastle, entropy can help explain why without intervention, controls decay. So here is my pile of sand. Taking the pile of sand representing our safety control as an example, entropy is a measure of how many ways I can rearrange the individual grains. The grains in the sand pile can be reordered and moved around without affecting the structure of the pile of sand. For this reason, the pile of sand has a high entropy. If we take the structured form of a sandcastle as our second example, there are approximately the same number of grains of sand in the sandcastle as there are in the pile of sand. However, very few alterations can be made to the sandcastle without damaging it. Almost any action will mess it up. For this reason, the sandcastle has a low entropy. So many ways to reorder the sand grains in the pile of sand is high entropy. Very few ways to reorder the grains of sand in the sandcastle is low entropy. If we leave our sandcastle representing our safety controls exposed to the elements, it's obvious that without intervention, our sandcastle, our control, will decay. As the wind picks up the grains of sand of in the sandcastle are stripped away. Now, Professor Bryant Cox tells us that there is nothing fundamental in the laws of physics that says the wind could not pick up sand and deposit it in precisely the shape of a sandcastle. There is no reason that this couldn't happen. It's just extremely, extremely unlikely, because there are very few ways of organising the sand so that it looks like a sandcastle. It is overwhelmingly more likely that the wind will take the low entropy state of the sandcastle and turn it into the high entropy state of a pile of sand. Entropy always increases because it's overwhelmingly more likely that it will. If we take the performance indicators from HSG 254, we can begin to look at the barriers not as solid single objects, but as the many individual components that make up the barrier in the same way that grains of sand make up the sandcastle. So let's strip away the incident, hazard, and consequence so we can consider the barriers in isolation. It is widely accepted that barriers used by industry to prevent harm are in constant decay. Identifying barriers in a high entropy state after an incident is too costly, regardless of how the cost is measured. Preventing an incident requires a mechanism that is capable of monitoring the condition of barriers and providing advanced warning of an increase in entropy such that the control can be maintained effectively. This is what the performance indicator must help us understand. Reporting lead performance indicators requires focused monitoring of critical controls to ensure their continued effectiveness. The performance indicators shown here are represented graphically using a tachometer. The tachometer is a common choice in guidance material and in industry for depicting performance indicators. The integer used to score the performance indicator has been represented in percentage terms. This concept has been borrowed from the Centre for Chemical Process Safety Guidance for process safety leading and lagging metrics. The concept allows for a simple calculation that represents the performance indicator as a measure of goodness. As we move to a specific example for the Mulwala facility, our operating instructions used by operators are controlled documents at the Australian Munitions Facility used to document production processes. These documents are reviewed in accordance with new timelines set out in the Health, Safety, Environment Management System for the facility. The tachometer on the bottom right displays the percentage of operating instructions which have been reviewed and revised and approved within the desired period. This is displayed as operating instruction in date using the calculation number of operating instructions past due divided by the total number of operating instructions. This formulation can be found in the Health and Safety Executive 2016, number 19, and the OECD 2008 guidance material. The tachometer is accompanied by a threshold matrix on the left, represented as a bar chart. This metric displays for each individual department the percentage of operating instructions in date for the reporting period. The tolerance level for each threshold matrix, which is indicated in red, orange, and green, is set at the same level as the threshold in the tachometer. When the level for the reporting period falls below the tolerance level, corrective action should be taken. In this circumstance, corrective action is assigned via a management review meeting. A critical element of operating procedures is to ensure the procedures contain the correct scope. The process for review and approval of an operating instruction is tied to the layers of protection analysis study used for each production process at the Mulwala facility. The LOPA facilitator is a risk engineer that is also assigned as a reviewer of the operating instruction. In this way, each operating instruction review includes an independent review aimed at ensuring procedures contain the correct scope. The operating instruction expiry and review is managed in a centralised document control system, and the output from this system feeds the performance indicator. Operating instructions at the Australian Munitions Mulwala facility make use of operator check sheets. The operator check sheets are used to record product transfer information, to confirm that pumps are in the appropriate run condition, valves have sequenced correctly, and in some cases, that product transfer has been visually confirmed. If we go back to our guidance material for a moment, HSG 254 nominates a communication lead indicator as the percentage of post-transfer checks undertaken to confirm that pumps have stopped and valves are isolated or closed. In order to monitor this, we have introduced an inspection program that rates elements of the operator check sheets as to standard or not to standard. This is displayed as operator check sheets percent standard in the tachometer and in the departmental threshold matrix. The inspection program reviews and rates each data entry point on the operator check sheets. This gives every data point used by the operator the opportunity to be rated as to standard, not to standard, or as not applicable. This allows the performance indicator measurement to track up or down as individual elements of the operator check sheet improve or decay. In this way, measurement is closer to the individual grains of sand in our sandcastle analogy. An important element of the operator check sheet inspection program is the immediate feedback provided to the operators at the time of the assessment. The operator check sheet inspection also contains a qualitative assessment of the operator's understanding of checks they are performing. This assessment is not currently rolled up into the performance metric. As we follow our operator through the routine production activities, we must ensure the operator has the required level of competency. HSG 254 nominates a staff competence lead indicator as the percentage of staff who have the required level of competence necessary for the successful transfer and storage of products. To monitor this, the Mulwala facility developed a custom-built competency management system, referred to as the CMS. Competencies in the CMS are categorised as on-the-job and off-the-job training. On-the-job training is the category that refers to the training and competency assessments that are conducted in the field or on the job. The system ensures that all training, accreditations and licenses are and remain current and provides an opportunity to forward plan site training requirements. The shift matrix, which is pictured on this slide, is an essential function of the CMS which enables shift leaders, schedulers and other personnel to generate a shift report. The report compares individual employees against operator competency. Competency expiry and competency assessment records are all updated in the CMS. When we looked at a performance metric for staff competency, we created the Operator Critical Action Assessment. The Operator Critical Action Assessment is the most labour intensive of our checks. To create this check, we went back to our LOPA study. The process requires that our MHF risk assessments have adequately detailed the operator critical action in a process. In order to populate the audit checklist, we pull the operator critical actions from the LOPA. To enable the transfer of these actions into a checklist with questions, the actions must be clearly detailed in the LOPA. If a risk assessment does not contain a clear account of operator critical actions, we use this as an opportunity to update the LOPA. As part of the preparation work, we also check that the operator critical actions in the risk assessment are accurately reflected in the operating instruction. If the operating instruction is missing operator critical actions, we use this as an opportunity to update the operating instruction and the status of the action in the LOPA. And lastly, we test the operator in the field to ensure they are aware of the critical actions they must perform. This is done by asking the operator how they would respond or what is required in certain circumstances. Based on the operator's response, the operator is deemed to be fully aware, partially aware, or not aware. This is recorded and feedback is then given to the operator, the team leader, or supervisor. Measuring staff competency in this way created a bottom-up assessment of the operator knowledge, and in doing so also identified any gaps that exist between operator competence, the operator procedure, and the layers of protection analysis study. As we leave our operator now, we turn to the equipment that the operator uses. And of course, that equipment must be maintained. Reoccurring maintenance actions are scheduled with the preventive maintenance module of a computerised maintenance management system. A subset of PMs are rated as safety critical. The determination process for a safety critical PM is made as part of a layers of protection analysis study. Safety critical PMs are scheduled preferentially during the creation of a maintenance schedule. This simple act of treating safety critical work orders favourably in the maintenance schedule process provides a higher level of assurance that these work orders are completed within the scheduled time period. The percentage of safety critical maintenance actions identified which are completed specific timescales are displayed as safety critical work orders percent in date, using the calculation number of safety critical work orders past due date divided by the total number of safety critical work orders. Safety critical PM work orders are identified in the computerised maintenance management system, and these PM work orders are categorised by work group, which is a subset of department. Safety critical PM include work orders that address emergency arrangements. This includes the maintenance of fire detection and suppression, as well as PM work orders tasked to the emergency response team to conduct drills or to inspect their equipment. The percentage of critical emergency arrangement related PM work orders is included in the calculation of critical work orders past due date divided by the number of safety critical work orders. Safety critical PM work orders include work orders that address instrumentation and alarms. This allows the measurement of safety critical instrumentation and alarm activities. The percentage of functional tests of safety critical instrumentation and alarms to schedule is included in the calculation of safety critical work orders. The Australian Munitions Mulwala facility defines safety critical control as a control that significantly reduces the risk of a major incident. The determination process for a safety critical control PM work order is made as part of the layers of protection analysis study. All safety critical control PM work orders are mapped directly to a control or controls in the local study. The safety critical control flag, pictured on the bottom right, allows all layers of the organisation, including the trade carrying out the work, to be fully informed of the fact that they are working on a safety critical control. Non-routine work at the Australian Munitions Mulwala facility is approved through the use of a permitting process. The authority to approve permits is delegated via a permit authority matrix. A regular permit inspection program rates elements of the permit as to standard or not to standard. This is displayed as permits percent to standard in the tachometer on the bottom right and the threshold metrics on the left. The tachometer and threshold metrics is accompanied by a trended metrics shown on the top right. The trended metrics uses the same calculation. However, the trended metric shows the change in performance measure value for the reporting period over time. HSC UK guidance material on the permit to work system was used as a basis for determining work permit assessment criteria at the Australian Munitions Mulwala facility. Permit inspection program is undertaken using the check sheet. The Health and Safety Executive UK guidance on permit to work systems covers the review of both permit records and work conducted in the field against the permit. The Australian Munitions Performance Indicator is divided into two separate permit inspection programs. One program inspects permit records after completion. The second reviews and assesses the work in progress in the field. The review of non-routine work completed under permit in the field reviews an individual permit against 19 separate assessment criteria adapted from the Health and Safety Executive UK guidance on permit to work system. Each criteria is rated as to standard or not to standard. The assessment of each permit reviewed is rolled up by department and for the whole site for each reporting period. The performance metric is displayed as permit field work percent to standard in the tachometer and the threshold metrics. The performance indicators are consistently presented with site performance as a tachometer and a threshold matrix by department represented as a bar chart. The individual threshold matrix aims to utilise social motivation as a mechanism for generating a willingness to take action when a performance metric falls below an acceptable level. Here we can see the field checklist criteria on the left and the records checklist criteria on the right. These are the two checklists that were created from guidance material and adapted for the site and separated so that we have the two performance measures. In summary, a lot of effort is put into risk assessments, LOPAs and QRAs. However, we must also understand if the controls we put so much effort into identifying and creating are still in place and effective, or are they more like sandcastles blowing away in the wind? Thank you.
Thank you, Adrian. Insightful, so thank you very much for that. And that is all the time we have. Adrian, thank you very much again for being so generous with your time and for your very insightful presentation.